Today we're going to work out a problem from Academic Excellence Workshop number 4. So this is worksheet 4, problem number 1. So basically what's going on in this problem is we've got a weasel and he's sitting out here on a merry-go-round, and at some time a tanuki just runs out of nowhere and comes and spins the wheel trying to make him slip. And he spins it at a rate of 2 radians per second. So what we have to do is find out, will the weasel slip as a result of this spinning? And so how are we going to do that? I guess the first thing we're going to do is the same thing we always do, and that's draw a Freebody diagram. So I'm going to draw this from the side view, so like we're standing off at the edge and we're looking at the weasel from the side. So let's say that's the weasel. I'm going to say my system is the weasel. And I'm going to say, like, over here is the center, just so you know. Well, I've still got the same thing as usual. I've got a normal force from the merry-go-round pointing up. And, of course, I've got a weight force pulling down. But then we have to ask, well, he's going in a circle, so we know we must have some sort of force in the centripetal direction. And it's, of course, not one of these two. So what is it? And it turns out in this case to be static friction. So it's the static friction from the merry-go-round that's always pushing inwards and causing him to move around in this circle. So I'll go ahead and draw that right here. Okay. So now we say, all right, we've got this Freebody diagram. Now how do we find out whether he's going to slip or not? Well, that turns out to be using the same methodology we used before, and that's we find out what sort of static friction is necessary to make this sort of thing happen, and if that's possible, then it won't slip, because if it doesn't have to slip, nature's not going to let it slip. So what do? We say, all right, I've got a centripetal force now, so why don't I use Newton's second law? I could say the sum of forces in the centripetal direction equals mass times acceleration in the centripetal direction. So using the weasel again as my system, and calling this the positive centripetal direction towards the center, I'll say static friction, and that's the only force in the centripetal direction, so that is the sum, equals the mass of the weasel times centripetal acceleration. I happen to know these really useful formulas when dealing with centripetal acceleration, and I know that it happens to equal omega squared r, where r is the distance, not the radius necessarily of the merry-go-round, but the distance from the center that the weasel is sitting at. And I just happen to label that one r2. So now we've got this this expression already. We've got everything here, so we can just plug it in and find out the static friction necessary to hold him on. So now the question is that possible? So to do that, we do the same thing we always do. We find the maximum possible static friction force, which we know is just equal to mu sub s times the normal force. And since we can see from this picture, he's not accelerating up or down, so normal must be equal to weight, like it often is, we'll say static friction max equals mu sub s times mg. And so if we take these two and we plug in these values that I've written over here, we can find out eventually that the static friction force necessary is actually greater than the maximum possible static friction force. And since it requires more than is possible, we know it's not going to be able to hold on to the weasel, and he is going to slip.